Let's start today's tutorial, everyone. Today's tutorial is actually gonna be easy. Last week's tutorial was the hardest among all. So, in case y'all haven't noticed, the tutorial recording is already out. I took 2 hours to explain that one question, so please feel free to look through. I have been complaining to YouTube as to why timestamp is not working, but in case y'all want to jump, I already put the timestamps here also. Because it's a long video, so y'all can just see which part you want to review more. Okay, so today let's discuss about, actually this one is quite easy, but this, I am confident this will be in the final exam because that is when the true or false question will come in. Okay, so we are going to talk about kernels, specifically on kernel functions and also how the kernel trick applies to SVM. Remember that in last week, we discussed that after we see about all the complementary slackness, right, the entire SVM will only boil down to basically the dot product of this x that is part of your support factors times any unknown factor, right? Okay, remember that last week we discussed that it will boil down to just the dot product of these things. Okay, so one of the problems that SVM failed to handle is that what happens when the data itself is separable, just that it's not linearly separable. Okay, so you will have some data that looks like this. Let's say this is let's say this is your data, then you will have data points that look like this. You want to separate out the red and blue separately. Okay, in fact, for those who still remember this from 2109S, this is exactly what you call the XOR problem. Okay, so the XOR problem cannot be solved by a normal SVM solely because the decision boundary is not linearly separable. Okay, both of these data is not linearly separable. But there is actually another way, so that what if we can try to increase the dimension in such a way that if this would become like, say, a 3-dimensional kind of thing, right? Then if I put my blue points at one plane, then my red point will be at some other plane, right? That I can slice them in between, if you see the logic here. So in a way, I want to kind of bring them up. Okay, that is essentially what we mean by having, like, say, feature engineering, which is in SVMs, that is how we apply the kernel functions. Okay, so this kernel function, in essence, is actually, it tries to build up more features for your factor. Right now, your input, say, only contains 2 dimensions, then what if I want to extend to another dimension? Okay, so if I have a mapping that contains, basically if I have a mapping that takes in any point within this domain, bring it down to the second domain here that I can separate them. This is basically what your function does. Okay, so because we are only concerned with the dot product of the support factor with any unknown factor, we can actually just apply it directly to our kernel mapping here. So this will be the dot product of the 2 kernel factors. Okay, so far questions on this? Thus, in the lecture, we also discussed about the 2 criteria for a kernel. The first criteria is that for it to be a good kernel function, for it to be an actual kernel function, it can be separated into 2 separate factors. Okay, so now this will look like, this will be the dot product of 2 factors actually. Okay, if you notice, this is just the dot product. So notice that the phi itself, this is your kernels. Both of these are factors. Okay, both of these are factors. When you take the dot product of 2 factors, the resulting item will be a scalar. That's why your k of xi, xj, this will be a scalar. Okay, questions? That's the first criteria, the main criteria. Or you can also use the alternative method. That is, if I map my kernel function here as like kind of a matrix, then this kernel matrix, if I take any factor, okay, I transpose this factor, I multiply with the kernel matrix, then I multiply back to this factor, this must be greater than equal to 0. Okay, this is basically what we mean by the kernel matrix must be positive semi-definite. Okay, so these are 2 ways that you can use to identify whether something is a kernel or not. So the general definition is just that a kernel function is so I can split them into 2 separate factors. Okay, that's the general one. But another criteria you can use is just if it's easier for you to compute the kernel matrix, then you can use the positive semi-definite property. Okay, any questions? Okay, so now let's move on to the first problem. So the first problem is we assume that we have 2 factors, x and x prime, both of them are of the same dimension. We want to prove that if ka and kb both are kernels, then the following new functions are also kernels. Okay, first one we will see, what if we have some function that takes in a factor returns you a real number. So this is, if you know the terminology, this is what we call a scalar function. Okay, essentially it's just a function that returns you a scalar. Okay, a real number here. Okay, so what if you have a kernel? In front of it, you multiply by the scalar function taking x. After it, you multiply by the scalar function taking x prime. The question is this a kernel? Sorry, the question is this is a kernel, but how do you prove that this is a kernel? Okay, so for this, I will use basically the first definition here. If I have a kernel, if I can split them into two separate kernels, then I'm okay. Okay, so let's try to see here. This Ka is a kernel, right? Based on the definition of the problem. So Ka itself is a kernel. That means I can separate this out into two separate kernel mappings. So I can have this is my first function. This is the second one. Okay. So essentially this is just the dot product of the two. Okay. So this phi A is essentially the kernel mapping associated to kernel Ka. So when I do this, then I will see I can just bring down the fx as well as the f of x prime. Now you should already see something unique here. Since both fx and fx prime are basically scalar functions, so I can actually multiply them to each of the factor directly. So this is my fx, multiply them to the first factor. This will be transpose. Then the second one would be just the phi a x prime, fx prime. Okay, because these are just scalar multiplications. Or rather, I can actually bring the fx prime in front of the phi a also, and that's okay. Now the moment this happens, I can now construct a new mapping. We set, this is our phi 1. Phi 1 is basically the kernel mapping associated to the first kernel, K1. Okay, so this is my mapping. So I set phi 1 of x. If I have this, then I will just take in the x. I return basically fx with phi a x. Okay, so I set a new kernel mapping phi 1. What it does is basically I am going to multiply fx with phi a of x. Okay, so then I notice that this part is just phi 1. This one is just phi 1 of x. This part is just phi 1 of x prime. So now this will become, let me just write here. This part will just become phi 1 of x transpose phi 1 of x prime. By definition, now we already have a kernel. Okay, any questions on this? So what I did here is just basically I used the definition of a kernel to deconstruct your Ka into your phi a and phi a. Okay, phi a of x and phi a of x prime. Then afterwards, I try to construct a new mapping so that I can rewrite K1 in terms of two kernel mappings. That's basically the goal of this problem. Okay. Now we move on to the second part. The second part is basically, we want to see if you try to add two kernels together, this will still be a kernel. Okay, so K2 of x and x prime is just basically the sum of Ka and Kb. So here here is where I will actually show you two different methods to do. First one is we use the general kernel definition. So the general def. Here I can again separate Ka and Kb to its own kernel mappings. So here I will separate this out to be, this will be phi a of x transpose phi a of x prime, plus this will be phi b of x transpose phi b of x prime. Okay, just for this tutorial I will skip the arrowhead because everything is a factor lah. Okay, so it's easier for me to write also. So this will be just phi a of x dot product phi a of x prime. This will be phi b of x dot product phi b of x prime. Okay, now how do we make a kernel out of this? The key idea now is the moment you have this, your goal is to see how can you construct a dot product out of this equation. Okay, so I repeat, the idea is how to construct a dot product. That's the first key idea. The second one is you want to isolate anything with x together into one factor, anything with x prime together into one factor. So basically we want to separate it out so that anything associated with x is on one single factor, anything associated with x prime is on another factor. Okay, so if you notice, this is basically a multiplication, right? Phi a of x multiply phi a of x prime. Then this one is just phi b of x multiply phi b of x prime. Both of them are factors, right, in a sense. Okay, so if I can see that this is just multiplication plus multiplication. So in the nature, I can actually separate this out into a dot product. How is it? I see that, let me just give another color. This is the one associated with x. Then this is the one associated with x prime. Okay? So if I want to construct this as a dot product, then I can have something like this. This will be my first factor that will be associated with x. Okay? This will be the first factor associated with x. Then I will do a dot product with this, the factor that is associated with x prime. Okay? Because the moment this happens, then it will just be a dot product of, if you separate this out, then it will be this dot product with this dot product with this, you sum up the result. Okay? So that is how you separate out into the two separate factors. So this is the factor that corresponds to your x. This is the factor that corresponds to your x prime. Okay? So with this, then we can now put in the kernel definition again here. So we try to set a new kernel. We set this will be our phi 2. Phi 2 of x would basically be, I will construct a factor that will contain, this is the factor of x, a factor of phi a. This will be the factor phi b. Okay, so this in itself is a factor of dimension, basically the dimension of a plus dimension of b. Okay, so I basically stack phi a and phi b together. The moment that happens, then I can just dot product them together. Okay, so when this happens, then I will just put in the definition here that this is just phi 2 of x dot product with phi 2 of x prime. And now we have shown that this is a kernel. Okay, any questions? I will show you the second way of doing this. Because this is actually an addition, right? So the kernel matrix itself is actually quite easy to construct. Here we will try to see whether we can prove this by showing that the kernel matrix is positive semi-definite. So in this case, I can put, let's take capital K2, this is our kernel matrix, is equal to the sum of the two kernel matrix, Ka and Kb. Because this is just the sum of kernels, right? So the kernel matrix of this is just going to be the sum of kernel matrix for A plus kernel matrix of B. So what I need to show, that if I take any factor V, I multiply with the kernel K2 and V, this must be greater than or equal to 0 for any possible factor. Okay, so this is my goal. Any factor multiplied by K2 multiplied by that factor again must be greater than or equal to 0. So this is my goal. Now we'll see. This phi transpose K2V, this part is essentially equal to saying this is phi transpose Ka plus Kb phi. Okay. Now I can apply the distributive properties. If I left multiply phi t to Ka plus Kb, then this is just the same thing as I do phi t of Ka plus phi transpose of Kb times phi. Okay. Then I do the same distributive property again. Now this will be phi transpose Kav plus phi transpose of Kb phi. Okay, so this is after I expand using the distributive law. Now the moment this happens, I notice that Ka and Kb both are kernels. So because Ka is a kernel, this part is going to be guaranteed to be greater than 0. Okay, because Ka is positive semi-definite, it's a kernel. Same goes with this part. This part is going to be greater than or equal to 0 also, because Kb is also a kernel by definition of the problem. So the moment this happens, then I will know that this will be greater than or equal to 0. Thus, I know K2 is going to be positive semi-definite. PSD. Okay, any questions? Okay, now we go to the last one. If I take two kernels, if I multiply them, the resulting output is also a kernel. Now this one is actually a bit tricky. In fact, this is the hardest problem of the day, I think. Okay, so if you are lost anyway, just raise your hand, let me know. So we want to show that if I multiply two kernels, this will give me the same kernel. This will give me a kernel as well. Okay. Here I will use back the general kernel definition. I will separate them out into separate kernels, separate kernel mappings. So phi A and phi B again. Here I will separate them out into, this is saying, this is the dot product of phi A with dot product with the x prime. then I'm going to multiply this by phi b of x transpose phi b of x prime. Okay. Quick question, why is there no, why I didn't put a transpose here? Anyone? Just a sanity check. Why is this not transpose here? Because remember that your kernel itself will output you a scalar value, right? So this is just a scalar multiplication actually. Okay? The only dot product is actually between these two circled one are dot product. But after this will be a scalar. This will be a scalar also. So I'm doing a multiplication of two scalars. Okay? So just to keep that in mind. Here, for me to actually drill this down further, I want to group together your phi of x and phi b of x, okay? So I want to group x in one side, x prime in another side. That's my goal. But if I do it like this, it will be very hard to separate because now this internal is a dot product with this, right? Whereas this is a dot product with this. So for me to actually separate out the x and the x prime, I will have to split the dot product itself. This is where I will go deep into the element wise of each phi a and phi b. Okay, so if I try to rewrite the dot product in terms of an element wise multiplication, then I can have this will be basically say, we suppose that capital N is going to be the dimension of phi a. So this will be phi a of x n, phi a of x prime n. So this is telling me I'm multiplying element n of phi a x with element n of phi a x prime. Okay, so I'm iterating from 0, 1, 2, 3, 4, 5, so on and so forth. Once I finish this multiplication, then I will multiply with this. I will put a separate number here. So this is to multiply with what with the element-wise multiplication. Capital M, I will set this as the dimension of phi b. So this will be phi b of x, element m, phi b of x prime, the mth element of this. Okay, any questions? So I'm just going to rewrite the dot product in terms of element-wise, in terms of the sum of the product of element-wise multiplication. Okay, any questions? Now I notice that this is just, I have a sum, then technically I can just put them together into, because I'm multiplying, right? So in the end I can just combine them into one huge sum here. So this will be n equals to 1 up to capital N. This will be m equals to 1 up to capital M. So this will be phi a of xn. I multiply by phi b of xm. Then this will be phi a of x prime and phi b of x prime m. Okay, because this is a summation. Then I'm just doing a multiplication. I notice that this part will depend on the n, this part will depend on the m. So I can write this as a double sum. Okay, questions on this? Now the moment this happens, I realize that once I combine them into a double sum, now I can combine these two things together. Okay, now I can kind of group these two things together because now this part on my left hand side, on my left group here, the left group is only containing your x, whereas the right group is only containing your x prime. So by logic, if I would have a kernel mapping, I want it so that, okay, if I have a kernel mapping, I want it so that this will be my, say, let me call me this by phi 3. My phi 3 of x would be basically phi a of x, phi b of x, something like this. Okay, but then the dimensions might be different because now this will be depending on my dimension of phi a. This will be depending on the dimension of phi b. Okay, so this is kind of the nm element of this kind of thing. Okay, so this is where it might get a bit complicated. So we are going to define a new thing. We will define a very large matrix first. So we are going to set this capital phi of x. We will set this as a 2D matrix. Okay, we will set this as a 2D matrix such that if I have element ij of this 2D matrix, this is just taking what is the ith element of my phi a, multiply this by the jth element of the phi b. Okay, so notice that this is just basically kind of I construct a 2D matrix, that is I multiply the ith element of phi a with the jth element of phi b. That's my ijth entry of the 2D matrix. Okay? Questions on this? I think this should be n times m, sorry. Yeah, it's more like it. Questions? Now comes to the interesting one. How do we set your phi 3? So we are going to set phi 3 of x. Instead of it being a 2D matrix, because I want my kernel to be a factor, right? I want my kernel to be a factor. So what I'm doing now is I will set my phi 3 to be basically a flattening of the initial 2D matrix. So how do we do this? Let's say if I have a matrix 1, 2, 3, 4, 5, 6. Okay, this is my 2D matrix. This is a 2 times 3 matrix, right? So my phi 3 would be basically, this will be a factor that contains 1, 2, 3, 4, 5, 6. Essentially, I will flatten this out into a single dimensional factor. Okay? So thus the dimension of this phi 3 is essentially how many rows times how many columns, because that's the number of elements you will have. That's why this will be m times n. So this will be mn directly as a one dimension, instead of it to be a cross product of two separate fields. Okay? Questions on this? So my phi 3 is essentially, I repeat, this is my 2D factor, right? My 2D factor, I will just basically flatten out into one single factor. Okay, your 2D matrix becomes one single factor. That's my phi 3. So at this point, this phi 3 itself, let's call this element, this phi 3 itself will basically be all of the elements of phi xij in its own order. Okay, so this whole thing will actually be, from this whole double sum, right? It will look like this. If I use the capital phi, now this will look like I will just take capital phi of x nm, then another capital phi of here, this will be x prime nm, right? Okay, because this one I will just write this as this will be the x capital phi, this will be the capital phi of x prime. Okay, so I'm doing now is basically from these two separate, from these two separate capital phis, which is your 2D matrix, I want to get for every single element-wise multiplication. Okay, this is my phi x. Okay, this is my capital phi x, your 2D matrix of x. This is your capital phi x prime, your 2D matrix of x prime. I take the element-wise multiplication of each item, which essentially, if I flatten them up into one single factor, is just basically a dot product of these two factors. Okay, so I can write this as similar to saying this will be from I equals to 1 up to m times n of this will be your phi 3 of xi, phi 3 of x prime I. This is after you flatten them out. Okay, which in the end, this will just be basically phi 3 of x transpose phi 3 of x prime. Now I can write this as a dot product by definition. Okay, any questions? No questions? Okay, now we'll move on to the second part here. So the second part is we are still going to do some proving. The first question is we want to prove that a polynomial kernel is indeed a kernel. How do we define a polynomial kernel? We see, for example, this is one of the case of a mapping. Your phi x is equal to 1 square of 3x, square of 3x squared, and x cubed. Okay, so the moment that I try to take a dot product of two factors here, say x and z, then if I multiply them, this will be 1 plus 3x z plus 3x squared z squared plus x cubed z cubed. Which in the end, if you remember the binomial theorem, you can separate them out into saying this is just 1 plus z xz raised to 3. Okay, so you see that from a linear x, I'm able to increase the dimensions. Okay, from taking a linear x, I can increase the dimensions to x squared, x3, so on and so forth. So that's the function of a polynomial kernel. Now we take a very general case. If we generalize it to an arbitrary dimension of d and arbitrary degree of p here, we want to show that a polynomial kernel is defined by 1 plus x dot product z raised to p, where p is just any p is basically any non-negative degree. Okay, oh sorry, a natural number degree, so positive degree. We want to show that k poly is indeed the kernel. Now how do we do this? Okay. So for this, I will be explaining 3 different solutions. Depends on which one is more comfortable with you. Because in the end, one of your exam questions can be, if this is the kernel, your goal is to determine whether it's a kernel or not. Okay, so then use whichever method that is more convenient to you. So the first method is essentially, we see that this K poly is going to be this 1 plus X transpose Z raised to P, right? Okay, so what I can do now is I can expand this into summations. Okay, I can actually expand this. So I can apply the binomial theorem. By the binomial theorem, I remember that, this one is, if you learn JC and I think MA 1521, you will notice that this will be basically sum from I equals 0 up to the degree. This will be the combination Pi. Then this will be xtz raised to that degree. Okay, so this is by binomial theorem. So then I can always construct a kernel mapping. My kernel mapping now would be such that the ith element of this kernel mapping will just be this whole thing, my xtz raised to I, but the coefficient here, I have to do a square root. So that the moment I multiply with another kernel, when I do the dot product, the square root will cancel out each other. Okay, so root times root, the root will take off of the same element. Okay, you notice here that this is 1, 3, 3, 1, right? So then the kernel will be square of 3, square of 3, square of 1, kind of thing. Okay, so now this will be, I will just put this. So now this will be just square root of the combination, multiply this by x transpose z I. Okay, so now I already constructed a kernel mapping. Then I can say that this K poly of x and z is just basically phi x transpose phi z. Then by definition, this is a kernel. Okay, questions? So this is the first method using the actual kernel definition. But in most cases, it might be a bit hard to deconstruct this part, right? Okay, so then we go to the second solution. So the second solution is you try to use the common theorems that is already provided to you. Okay, so don't know whether my OneDrive is already there. Okay, anyways, you can always go to whichever the, what is it called? Basically the book section 6.15 will actually show you what is the theorems for determining kernels. Then here you can just copy it directly. So I would say that this is the most important part to include in your cheat sheet. Yes, this one. Please make sure that you will include this in the cheat sheet for your finals. Or, sorry, you cannot use a cheat sheet, so make sure that someone included this in the collaborative notes already. This is very, 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 very important. Okay, so these are basically your theorems to determine whether it's a kernel or not. Basically, you assume that K1, K2 are kernels. Then you see how I can